Cockrell School has this Endowed lecture series where we bring in people to give a talk on something relevant. In the case of Onur, he has so much to say that I figured that it doesn't matter how fast he talks, he can't get it all in one lecture. So we're going to do 3 lectures instead on memory systems, which is the focus of his work recently. His first talk is right now. Tomorrow, Thursday at 3:30 in this room, and then Friday at 2:30, and I've forgotten the room number, but it's posted all over so you can find it. Onur is one of our own graduates after an incredible record of undergraduate work at Michigan. In fact, when he applied here for graduate school, did his transcript, and he double majored in double E, and what was the other one? Psychology? Yeah. And in the psychology courses, he only got A. But in the double E courses, he got A+. And as you go through the transcript, it's kind of interesting that all the double E courses were A+, all the psych courses were A. He came here for graduate work. He won the Provost Outstanding Dissertation Award from here before he graduated. Went on to Microsoft Research, then Carnegie Mellon. Carnegie Mellon established a special endowed chair just to keep him at Carnegie Mellon, the Strecker chair. But he finally decided to leave, and he has been for the last couple of years a senior professor at ETH in Zurich, one of the top institutions in Europe. And I think I'll shut up now and let you take over.
Okay, thank you very much, Yale, for the nice introduction. And thank you very much for coming here. It's actually a pleasure to be here. I've never seen this building before. When I was here, it was a very different building. Probably many of you have not seen it. Or maybe you have, I don't know. And I think this is the first talk I'm giving at UT after some number of years, if you don't count the 75th birthday ceremony. Okay, as Yale said, I have a lot to say. We don't need to cover all of it. I distributed over 3 lectures, but I definitely have a lot more material than 3 lectures here. The first lecture is about memory trends and reliability and security. We'll see how much we'll cover. These are some of the current research focus areas that I'm working on. I just want to give you a brief overview. I work in computer architecture, hardware-software interface, bioinformatics, and security. We're going to talk a lot about memory, especially DRAM and maybe some emerging technologies, but I work in pretty much everything in systems. We're going to touch on the very interesting intersection and the trade-off between hardware security, energy efficiency, fault tolerance, and performance today. I think as technology scaling pushes us toward less and less reliable architectures, we have very interesting trade-offs to make. We're going to talk about system and architecture interaction, new execution models like processing inside memory, of which there are different flavors, and new interfaces to enable them. And naturally, we're going to talk about heterogeneous and parallel systems. I'm not going to touch on a lot of GPUs, but that's something we work on also. I will start with something that's close to my heart, and I'll give you the story, but this will be a motivating detour to motivate what comes next. Genome sequence analysis and assembly algorithms and architecture is something that we work on. And I'll use this as an example to motivate. If you don't understand what I talk about, that's okay, because I'm going to go through it really fast. It will mainly be motivational. And I also work on biologically inspired systems and system design for bio and medicine, but I'm not going to talk about that. I'd be happy to talk about it separate. These are 4 key directions that I intend to talk about over the course of 3 days. Basically, we'll start with security, reliability, safety, interesting intersection of them. And then we'll move on to more energy efficiency, memory-centric architectures. Hopefully we'll talk about low latency architectures and maybe architectures for genomics, medicine, and health. I'll use this last one to motivate. As I mentioned, we'll do a motivating detour on genome sequence analysis. I think this is a very, very interesting area, and we need to enable new systems that can do this much better. And my personal story is, this is basically what we wanted to do when I actually was at Microsoft Research, and I was hiking with one of my friends on Mount Rainier. We were talking about, he's a bioinformatician, and I didn't know anything about bioinformatics at the time. I still don't know anything about bioinformatics, probably. But we wanted to design an embedded device that can perform comprehensive genome analysis in real time, within a minute, let's say. Basically, you could answer questions like, genome analysis, of course, is very general, but you could answer questions like, which of these DNAs does this DNA segment match with, for identification purposes, or for other, maybe more important purposes. What is the likely genetic disposition of this patient to this drug? And you can imagine many, many other questions once you have sequenced someone's genome and you have that data available. But of course, at that time, this is 2007, the device even didn't exist. The technology didn't even exist to be embedded. These are actually huge sequencing machines. I'll show you pictures of it in a little bit. Basically, everybody has a DNA. I'm not going to go through this. It's actually the subject of a much longer talk. You have ACTGs, and these exist, as you know. The goal in DNA sequencing is to find a complete sequence of the base pairs, AC, GTs, in someone's DNA. The challenge is there is no machine that anyone has built so far that takes long DNA as input and gives you the complete sequence as output in a correct manner. Actually, there's no DNA, you cannot get the complete sequence today. All machines are essentially choppers. They chop the DNA into pieces and they identify relatively small pieces with some error rate, but they do not tell you how those pieces fit together. So essentially what you have is a computational puzzle. You have this 3.2 billion base pairs in human genome, and the choppers give you pieces of length, let's say 300 or so. And the computational puzzle is to figure out how to stitch together those pieces of 300 long to get the real 3.2 billion base pair long DNA. This is just one example. Of course, choppers, I liken this to untangling yarn balls. If you have a cat that's played with yarn balls, they all become tangled, and you chop them into pieces, and then you try to figure out which piece belongs to, you try to reconstruct the yarn ball, basically. And these are the choppers that chop the yarn balls today. Actually, I'm out of date probably already. This is a very powerful chopper. It's about $3 million. It gives you pieces of 300 base pairs length. Its error rate is very low, error meaning that it identifies this mostly correctly, it's 99.9%. But you have trade-offs. This didn't exist in 2007. Now we believe in technology. It exists since 2014. So this is about $1,000, $2,000. You can buy it and you can do the chopping yourself. It's good in the sense that it has long reads, meaning it gives you these pieces that are like 900,000 or 1 million base pairs long, but its error rates are very high. So you still have a big computational problem. So you basically have significant trade-offs among these machines. But essentially, the takeaway from the previous picture is that we know how to do this reasonably well today. Maybe we don't have this perfect sequencing machines, but we can actually do very, very high throughput sequencing. We can get data out very, very quickly. And the cost of it is very low today. Unfortunately, we're bottlenecked by stitching these pieces together to understand what we have at hand. What does the genome look like of a person? And that limits us from doing the future analysis, because now we want to ask the other questions. Now I've identified the genome. What can I do with it? What kind of dispositions that I have to diseases? And then that also limits scientific discovery. So this is what attracted us at that time. This is one example. You can do comparative genomics like this. You have these different species and you compare them once you construct the genomes of the different species, and you may find some new discovery. As I said, we're bottlenecked in mapping. We're basically bottlenecked in computational algorithms as well as architectures today. So when we first started, I'm going to give you a very quick overview of what we've done in the area without going into a lot of detail. I'd be happy to talk about it separately, but my goal is to really motivate that this problem is really a memory problem, and that's what we've seen in our results. So when we first started, we actually wanted to design the most comprehensive mapper to date, and we did. We published it in 2009 in this paper. It's online, you can use it. I'll give you a better version of it as the slides progress. Basically, this mapper is able to it's guaranteed to find all mappers. So whenever you have a 300 base pair thingy, let's say, a fragment, this mapper can find every location. So it's very sensitive. Some of the other mappers that exist cannot find these locations, especially when you specify an error rate. Because you don't want to find the exact matches. You want to find matches with some difference. Because nobody's genome is exactly the same as a reference genome. So it can tolerate up to some number of errors. The downside is, like with all mappers, this is slow. It's even slower because we want it to be very comprehensive, because you don't know what you're missing in this field if you miss some mappings. So it turns out it's bottlenecked by what is called read alignment. It's edit distance computation. You take this fragment and you compare it to different parts of the reference genome, and that needs to be edit distance computation because you want to find out the differences. How many insertions do you have? How many deletions do you have? How many substitutions do you have? This is, if you know Hamming distance, this is much worse than Hamming distance, because Hamming distance gives you a direct comparison of two equal length strings. Here you want to find the differences between the strings. And this mapper spends a lot of its time in doing edit distance computation. So our key idea at that time was to actually get rid of these computations as much as possible to begin with. The idea is build some index such that you can filter past quickly before you do this edit distance computation. Whenever you get a small fragment, check if it's going to match this location, any of the locations. I'm not going to tell you exactly how we do this, but this actually minimizes approximate string comparisons. And that's what we did in software first. Basically, you wanted to get rid of as much as computation as possible, and you can actually get rid of more than 99% of these edit distance computations by exploiting the structure of the genome, reference genome. Because you can quickly eliminate that this particular fragment you can guess quickly that this particular fragment is going to match or not match particular location if you built a good index of the genome. So this actually speeds up read mapping by 20x or so. It's purely software. We had some other ideas in software that I'm not going to go into, but then later we went into parallelizing this using SIMD, single instruction, multiple data instructions, data operations in existing machines. And this actually introduced a new metric shifted Hamming distance. It tries to do this approximate string comparison very quickly to design a much better filter, and this speeds up the mapping by about 3x more. And then we went into more hardware. We actually built the first FPGA-based alignment filtering mechanism. I'm not going to go into the detail, but you can actually download the source code and use it for yourself. This speeds up the read mapping by another 10x or so. What's the problem? Basically, all of these mechanisms are actually heavily bottlenecked by data load. Once you optimize the software to get rid of computation as much as possible with intelligent tricks, the FPGA performance is limited by the DRAM bandwidth. That's true for the SIMD performance with the shifted Hamming distance. So we're currently exploring more aggressive solutions that push the computation inside the memory. So processing in memory actually can alleviate the bottleneck, and we're going to talk about that during these lecture series. However, we need to design the mapping and filtering algorithms to fit processing in memory. This paper is one of the first attempts that we've done. It was published at the beginning of last year. That essentially looks into using 3D stacked memory as an accelerator to do the filtering, and the CPU does the rest of the computation that the memory is not very good at. I'll go through this very quickly. Basically, we exploited some principles to get to these results. You can exploit the structure of the genome to minimize computation, and you can morph and exploit the structure of the underlying hardware to maximize performance and efficiency. So essentially what we did is, what we've been doing is algorithm architecture co-design for DNA read mapping. And our results show that you can speed up DNA read mapping by about 200x, sometimes more, sometimes less. It's very input dependent. And you can improve the accuracy also. So I'm excited about, we were talking about embedded devices as our dream in the beginning. Now I'm excited about this because these devices exist, and there are a lot of bottlenecks in these devices. Today, this is a nanopore sequencing technology. Essentially, the DNA passes through nanoscale holes, and this device detects the current when different base pairs, different bases pass through those nanoscale holes, and then it attributes that current to ACTGs, for example. So there's a long pipeline. First of all, when you read the raw signal data, you want to understand whether it's an ACTG, and then there are a lot of algorithms that are employed over here to eventually get the assembly, the genome that you're looking for. I'm not going to go through this in detail, but if you're interested, you can read our paper. That was published again last year. So what I've been talking about so far is actually this part of the pipeline, which is read mapping. But depending on the technology, you may have bottlenecks in different parts of the pipeline. Okay, I don't want to make this a bioinformatics talk. I have actually a much longer talk related to this, and I'm not going to talk about that right now. But let's go back to what our dream was. Essentially, you wanted an embedded device that could perform comprehensive genome analysis within a minute, let's say. Where are we now? We still have a long ways to go. Actually, we're bottlenecked by energy, for sure. We're bottlenecked by performance, latency, and we haven't even tackled the security or privacy issues, which are important. And we found that there's a huge memory bottleneck in this particular application. So I've been telling you this because I think this is one potential application that could be enabled if we can overcome the memory bottleneck going forward. And I believe there are many, many other applications. This is an application area that I know some about, maybe not enough about, but at least I have an idea on this one. So now let me go into the other parts that we need to enable to actually enable such applications. I'm going to talk about memory and storage, mainly focusing on the main memory system. As you know, main memory is a critical component of all computing systems. Whatever we're designing, server, mobile, embedded, desktop, and sensor systems, we want to have some working storage in it. And this system must scale in many dimensions in terms of size, capacity, technology, efficiency, cost, and the algorithms we use to manage it if you want to maintain the performance growth and the scaling benefits we've been used to so far for a long time. And it doesn't matter what you attach, what kind of computing unit attached to this main memory, processors and caches, FPGAs, GPUs, or a heterogeneous combination of these, or different accelerators. We're essentially bottlenecked by memory today if you have data-intensive workloads. This is my quick picture of the main memory system. Basically, if you look at a node today, most of the system is dedicated to storing and moving data. Only these red parts over here are cores. Everything else is data storage and movement units, or control of the data storage and movement units. Caches, memory controllers, other caches, other memory controllers, shared memory, other interconnects, and storage. If you actually do the calculation, more than 80 to 90% of a system is dedicated to storing and moving data. We call these computing units, but computation is actually a very little part of the computing units today. It's very important, but we know how to do it really well. Maybe we don't know how to do memory really well. The second point over here is that most of the memory system is a shared resource across those computation units. We run many threads or applications, and they share the memory system, so you run into quality of service and predictability issues, which we will not talk about in these lectures, but that's also very important to solve. Let me give you in one slide the state of the main memory system as I see it today. There are some recent technology, architecture, and application trends that lead to some new requirements from the system, and that exacerbate some old requirements. We've always demanded a lot from the system, and we're going to demand a lot more. And I will hopefully show you that DRAM, the main memory technology that we've been used to for a long time, for more than 50 years now actually, and the memory controllers, as we design them, as we know them today, are unlikely to satisfy these requirements. And we're already falling behind, actually, in satisfying those requirements. And there's some emerging technologies, memory technologies, that happen to be non-volatile that enable new opportunities. And there are also emerging technologies that are DRAM-based as well, which we will talk about. Some of these opportunities may be memory and storage merging together, for example. I'm not going to talk a lot about this one in the lecture series, but that's an area I do work in also, and it's very exciting. Given these, I believe we need to rethink the main memory system and the system we're designing around it to fix the issues we're having with DRAM and to enable some of these emerging memory technologies, while of course satisfying all of the requirements. So this is kind of the agenda of 3 days. Basically, I'll first talk about the trends affecting main memory, and we'll talk about some of the key challenges and solution directions. Hopefully we'll cover 2.5 or 3. We won't be able to cover this emerging memory technologies part, unfortunately. And I will hopefully finish with some solution principles, and we will conclude. So this is in one slide, the trends that are affecting main memory. You could also flip this and say these are the requirements that we want. So essentially we want more memory capacity, more bandwidth, more quality of service, more performance out of memory. Energy and power is a key system design concern, true for memory. And technology scaling in DRAM, the main technology we use design memory with, is ending today. So let's talk about each of these a little bit. Essentially, we need more capacity, bandwidth, and quality of service, performance, because we know how to do computation well. We can fit many, many computation units and accelerators on a system, on a chip, and we're able to increase that. That's not a problem today. Applications are becoming increasingly data intensive. I gave you one example from bioinformatics. You can actually scale the data that you have in bioinformatics a lot, depending on the analysis that you want to do. And we want to consolidate more and more. We want to put basically more computation, more applications on a given area or on a given power budget as much as possible to improve our efficiency. And this is happening essentially in all systems that we have today. Let's take a look at one of the trends. This is the memory capacity gap. This is actually data from HP Labs at University of Michigan, published in ISPA 2009. These folks examined the trends of core count and memory capacity, and they showed that core count is increasing faster than memory capacity is increasing. And they also showed that memory capacity per core is expected to drop by 30% every 2 years, which is not good news for software, because software has always relied on having more memory per thread to get more features. So you could actually argue with all of these numbers over here, because it depends on where you collect the data. I believe this trend continues, especially in GPUs today. But if this trend is not continuing, it's a good question to ask, why is it not continuing? because we know how to do computation really well. We can stamp out these pores really well, but maybe we're not stamping them out as fast as before because we cannot feed them with enough memory capacity and bandwidth. So this trend is also related to memory capacity and bandwidth. So trends are actually much worse for memory bandwidth per core. Memory bandwidth is not increasing as fast as memory capacity today. And I'll give you an example of this. Let's have some fun with this figure over here. We're going to examine the DRAM capacity, bandwidth, and latency trends for a given DRAM chip. The most common chip of the day, DDR chip of the day, over the last 18 years. And we're going to look at the improvements in terms of how much capacity this device has, how much bandwidth, and how much latency. Can anybody guess how much capacity of a single chip improved over the last 18 years? Maybe the last 18 is not accurate because this ends at 2017 now. Any guesses? One brave.
100x?
That's good. That's a good guess. 128x. And this is the main driver of memory vendors. Memory vendors want to put more capacity per area. And that's what they optimize for foremost. And as you see, we're having difficulties in the last few years. And this is going to become worse. And I'm going to give you even more difficulties that we're having because of the drive for capacity. What about bandwidth? This is DDR technology. This doesn't look into the bifurcation that we're having with different technologies today for good reason. Any guesses? 4x. Yale said 4x. We're actually a little bit better. It's 20x. But bandwidth is, maybe we can increase it, but of course there are fundamental limitations over here, like pin count, for example. But with 3D stack technologies, bandwidth is increasing. What about latency? Somebody said slows down? I hope not. But actually it's close. Actually it does slow down in some technologies, that's right. But we have actually increased over time, we reduced the latency by about 30%. So this is clearly not the design point, but this is also hard to improve. So this graph is very telling because we're having difficulty even in the design criteria that we have, improving capacity as much as possible. And latency, which we're going to return to, is not doing very well over here. Okay. But DRAM is actually critical for performance. There are applications that we know more about that are limited by memory. Actually, all different bottlenecks in memory, latency, bandwidth, capacity. I think some of these are limited by all of them. And there are also other applications that we're going to get to as well, like consumer workloads, that are also limited by memory. So basically, if you're data intensive, you're limited by memory. Okay, in terms of performance. Let's take a look at energy very quickly. So energy is a key system design concern today. There's this beautiful paper from IBM Research in 2003 by Charles Leferge and others, where they showed that more than 40% of the entire system energy in IBM's big iron servers is spent on the off-chip memory hierarchy. And at that time, the off-chip memory hierarchy consisted of off-chip caches, off-chip interconnect, off-chip DRAM, and off-chip storage. Now fast forward about 10 years, IBM folks wrote a paper about Power 7, and they basically say more than 40% of the entire system power is spent in DRAM. That's true for the GPUs today also. Of course, you can argue with these numbers depending on the measurements, but essentially the power that's spent in the main memory is increasing because a lot of other things are going on chip, and the interconnect and the memory remains off chip. And DRAM consumes power even when it's not used, so we have a periodic refresh problem, which actually is one of the technology scaling issues that we have. So if you may have a lot of memory, you may not be using it, but you're refreshing it, so you're wasting a lot of power. Actually, my cell phones right now are doing self-refresh of memory and wasting power. So we recently analyzed, we're going to get back to this paper, but we recently analyzed these mobile workloads in Android devices and Chromebooks. And we've seen that more than 60% of the total system energy in these workloads are spent on data movements in the memory hierarchy. Okay, on top of this, DRAM memory technology scaling is ending. Basically, technology scaling means that you reduce the size of the circuit so that you can get more capacity in the same area. And you have a feature size of memory. You want to reduce the feature size of a memory cell, essentially. And ITRS, International Technology Roadmap of Semiconductors, which is an organization that has transformed into something else right now, they've been projecting for a long time that DRAM will not scale easily below X nanometers feature size. Of course, they don't say X, they have a number whenever they publish their report, but I don't want to keep my slide coherent with their reports. So we'll keep it as x. We'll get back to that x. Clearly, as you reduce x, you get higher capacity, you get lower cost, and you get reasonable energy scale, hopefully. But if this goes away, if technology scaling ends, then we're not going to be able to get these. As a result, we're not going to be able to satisfy all of these requirements over here. And we're already having problems with it, and I'm going to start talking about those problems. So DRAM scaling has already become increasingly difficult, actually. I'm not going to go into the details right now. I'll talk about it in a little bit. There are significant difficulties in manufacturing, in cell leakage, reliability. As a result, memory technology space has become more heterogeneous. So we have 3D stacked DRAM, for example, that provides higher bandwidth, reduced latency DRAM, maybe very high cost, but lower latency, low power DRAM, and emerging memory technologies that are non-volatile memory. If you look at that space, different technologies have different greens, advantages, but unfortunately they also have reds. So there's no single technology that's green at every metric that we want. They all come with trade-offs. As a result, designing systems that look like this, that have hybrid memory, is a good direction. This is already happening in the system design space. Basically, you have some memory technology that has some greens and some reds, and you have another memory technology that has some other greens and some other reds. Hopefully, they complement each other. And you design the data allocation and movement mechanisms in hardware and software to achieve the greens as much as possible while avoiding the reds as much as possible. And that's the idea of hybrid main memory. And there are a lot of interesting research in it that I'm not going to talk about in these lecture series. But one thing that's clear is you need intelligent controllers to actually take advantage of that sort of hybrid memory. Because an intelligent controller needs to understand where the data should be potentially placed and where the data should be moved. So this is going to be one of my motivators for what is coming next, because we're going to talk about computation and memory. And there will be reasons to actually design these intelligent controllers. And I believe this is one of the reasons. Okay, industry is actually writing papers about this too. This is one of my favorite papers that was written by Samsung and Intel, two companies that otherwise don't talk to each other. But they've written this paper in 2014 in the Memory Forum. And they've actually outlined nicely process scaling challenges. It's a 4-page paper. I would recommend people to read it if you're interested. They basically said it's too difficult to actually improve the scaling of DRAM, even though they're going to work on it and they're working on it. Refresh is a big problem. As you reduce the cell size, retention time becomes difficult to determine, and also retention leakage increases. As a result, you have a huge refresh problem. Actually, retention time becomes difficult to determine because you run into the variable retention time phenomenon, which is if you actually test the retention time of a DRAM cell right now, it may be 100 seconds, so it may have good retention time. But if you test it 100 seconds later, it may retain data for only 8 milliseconds. Why? Because there are these quantum-like, I like calling them quantum-like effects in very scale technologies where charge gets trapped in the access transistor, and once charge gets trapped in the access transistor, charge leaks out of the capacitor very quickly in the DRAM cell. As a result, you get very low retention times. It's very hard to find this phenomenon because this phenomenon happens to be a random process, and it may take days to actually observe this, maybe longer than days. And for that exact very reason, DRAM manufacturers are already adding error-correcting codes inside the main memory. This may or may not be a good solution, but I believe it's a good solution in this case. But what these folks from Samsung and Intel argued for, and what I'm going to argue for, what we've been arguing for a long time, is you could actually have intelligent controllers that could overcome some of these effects that are very difficult to overcome at the circuit and device levels. So they said architect controllers and DRAM together such that the defective technology becomes less defective because controller corrects these errors. And I'm going to give you examples of this in a little bit. This is going to happen more and more in the memory space. Okay, so I've given you the trends. Let's talk about some of the challenges and solution directions. I'm going to jump into reliability and security and robustness. Feel free to interrupt me if you have any questions. Okay, so let's start with this. Why do I start with this? Even though I didn't do too well in psychology, I've learned something at Michigan. I had actually very great teachers in psychology at Michigan. But this is a very famous American psychologist, Abraham Maslow, and this person dedicated his life into understanding why humans do the things they do, human motivation essentially. And he may not be famous for his face, but he's really famous for what he has done, which is essentially the hierarchy of needs. And you may have seen this picture at some point, especially if you've taken economics or psychology classes for sure. So basically, humans need to have their physiological and safety needs satisfied before they can think about highest forms of modern art or abstract art, for example. So you get the idea, hopefully. That's why we need to start with reliability and security. I think that's true for computers. We need to have working computers first before we can move on to high performance, extreme energy efficiency. I also like giving this example. Does anybody know where this bridge is? Tacoma Narrow. That's great, yeah. This bridge doesn't exist right now. It used to exist in 1940, but this is what happened to the bridge. Essentially, because of aerostatic flutter, there's an interesting story over here, but it broke. I give this picture because we're going to tie it to the memory in a little bit, because this is a reliability problem that's affecting safety and security, in my opinion. This is another picture that I like using. This is these folks are constructing Manhattan at a time, but maybe a bit flip in the structure will cause them all to fall, right? So I believe security is about preventing unforeseen consequences. It's a very general definition of security, of course. But I believe we need to think with this mindset going forward into the future. How do I prevent these folks from falling down if there's a bit flip down there? If there are computers, there are many bit flips. Okay, so how does this relate to the DRAM scaling problem? Let's go a little bit more into the detail of DRAM scaling. DRAM, like any other memory technology, requires two things to work. It needs to have a storage device. In case of DRAM, it's the capacitor, and it needs to have an access device. In case of DRAM, it's the access transistor, bitline, and the sense amplifiers. So both of these need to be reliable for this memory to work. The capacitor must be large enough for reliable sensing, access transistor must be large enough for leakage and high retention time. And this was the value that was assigned to X by ITRS in 2009. They said, reducing the feature size of the circuit below 35 nanometers is challenging. And they predicted that we would get to 35 nanometers in 2013. Today we're in 2019. What do you think is this feature size of a DRAM cell today? I know that there are people who can answer the question here. Anybody? Okay, I'll pick 16 right now. 16, 17 nanometers. But basically, we're much below 35 nanometers. Manufacturers have pushed this down significantly. But it has come at a cost. Basically, as we reduce the size of the cell, we're having reliability issues. This is one very large-scale study that we've done with Facebook. Basically, one of my students, Justin, who just recently graduated, they went to Facebook and analyzed all of the errors in their system. And they have a lot of memory in their system. There are a lot of servers. There's a lot of data in this paper, but I like showing this data. Basically, there's a strong correlation between the density of the chip employed in a server and the error rate that you observe in the server. This is a correlational study because we cannot control what's happening in all of the data centers. Clearly, chip density has a correlation with the failure rate. And that is like linear increase. Okay. Okay, I'd be happy to talk about that. So we've been studying this at the large scale, but we've been also studying this at the small scale. We built these FPGA-based infrastructures where you could have a memory controller and that can test memory. And we've been doing a lot of memory testing on real DRAM chips. And the reason we wanted to do this was we wanted to actually examine the refresh problem. We wanted to understand how we can solve the refresh problem, which is really one of the biggest scaling problems in DRAM. And we found a lot of interesting things while we were doing these studies. I'm going to tell you about some of those. And we actually open source, this is one of the infrastructures that we have at CMU. We recently open sourced this infrastructure, so you can actually download the code. We're not giving you the FPGA, but once you have an FPGA, you can actually do these studies for yourself. And we'd be happy to support this. So one of the things that you can find out if you have this sort of infrastructure is related to data retention. How long does a cell retain data in DRAM? Today, DRAM standards ask you to refresh all of memory every 64 milliseconds. Basically, every single cell needs to be refreshed every 64 milliseconds. Is that really necessary? If you look at the retention time profile of DRAM, you will see something like this. Basically, very few cells in DRAM require refresh every 64 milliseconds. Most of them, you can get away with refreshing every 256 milliseconds. Now, if you can do this characterization, understand which cell needs to be refreshed at what frequency, then you can actually get rid of, assuming this profile looks like this, you can get rid of more than 75% of the refreshes. Actually, around 75% of the refreshes, not more, depending on what parameters you choose over here, of course. Of course, it's not that easy, it turns out. We have a lot of studies related to this. I may talk about it if we have time. This is clearly dependent on the location of the cell. The retention time is dependent on the value that's in the cell and value of the cells around it because of capacitance coupling. And it's also dependent on time, as we discussed. The variable retention time phenomenon makes retention time dependent on time and makes it unpredictable. As a result, we have solutions to figure out this retention time profile. Now, how do you do this? It's very, very interesting. You need a online profiling mechanism. You need an intelligent memory controller that profiles DRAM in an online manner that I'd be happy to talk about separately. But the takeaway is, if you want to get rid of a lot of the refreshes, you need intelligent memory controllers. And I think that way you can actually scale memory to much smaller technology nodes. And that's essentially what Samsung and Intel was also arguing for, in my opinion. Okay, so while we were actually doing these studies, we stumbled upon very interesting things. And one of the things that was discovered by Jungo, one of my students, is you can predictably induce errors in most DRAM memory chips. This is called the DRAM row hammer problem. I'm going to focus on this a little bit more. This is a simple hardware failure mechanism that can create a widespread system security vulnerability. And I like this popular article by Andy Greenberg that says, "Forget software, now hackers are exploiting physics." And I like this because this actually really gets to the heart of the problem. Row hammer is a physical problem. So what's the problem? Memory consists of rows. Actually, this is a problem that's not just specific to DRAM, but when we describe it is going to be specific to DRAM, the failure mechanism. If you want to access a bit in a row, you need to activate the entire row, apply high voltage to that row. Now, if you want to access something else, you need to deactivate the row, basically apply low voltage to that word line or row. Now, if you keep doing this repeatedly, activate precharge, activate, applying low voltage is called precharge, activate precharge, activate precharge, activate precharge, activate precharge, enough times, before the cells get refreshed, it turns out in most modern DRAM chips, the adjacent rows have some bits that flip and that lose their data. We call this the hammered row, we call these the victim rows, and we examined many, many chips from 3 major manufacturers, who shall remain nameless, but you can guess who they are because there are only 3 major DRAM manufacturers. But we found that more than 80% of the chips that we've tested are actually vulnerable to this effect. And this is a scaling problem because this didn't happen before 2010. In the chips that we've tested that were manufactured before 2010, this effect didn't exist, or it existed, but it didn't get exposed to the system. Well, we'll talk about that in a little bit. Basically, all of the chips that we tested that were manufactured between 2012 and 2013 showed errors. And it's independent of the manufacturer. It's an industry-wide scaling problem. So why is this happening? Basically, this is because of the electrical coupling between the word lines. There are multiple effects that happen, but one intuitive way of explaining it is because of electromagnetic coupling. Whenever you activate one row, because there is not enough electrical isolation between adjacent rows, you're slightly activating the adjacent, physically adjacent row. And if you slightly activate the physically adjacent row, some of the vulnerable cells in that adjacent row that get connected to their bit lines, they lose charge a little bit. And if you do it enough times, before the cells get refreshed, you deplete the charge out of those vulnerable cells. And it turns out there are many, many of these vulnerable cells. I'm not going to go into the detail of the characterization over here. But let's talk about the higher level effects of this. Essentially, you can write a program that looks like this. This is a user level program that induces these errors. And we publish this code online. What this program does is it selects address X and Y such that they map to the same bank. And basically, ping-pongs activates. It avoids cache hits by flushing X from the cache, and it avoids row hits. And ping-pongs activates to X and Y. And if the chip is vulnerable, it will induce errors. Now our code is nice, but Google Project Zero later improved this code. They used an observation from our paper, and they selected X and Y such that one row was sandwiched between X and Y, so they were able to induce many, many more errors in real systems. And this is data from our paper. Basically, you can see that as long as you have a memory controller that can do these activations fast enough before the cells get refreshed, you get errors. And there's nothing special about Intel and AMD. All of the memory controllers that are out there are actually good enough to do these activates enough times before the cells get refreshed. Clearly, if the cells get refreshed more often, you can reduce this effect. Right? But remember, you don't want to refresh. Remember, you want to actually get rid of refreshes as opposed to refreshing cells more often. Okay, this is a real reliability and security issue. It actually exists in real applications also, but it's not very common, clearly. But it's more of a security issue. And when we actually wrote the paper, The first sentence we said was, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. I think it's very fundamental. And we said that you could actually design a program that could hijack the entire system. And while we were working on it, folks from Google Project Zero actually did exactly that. They showed that you could exploit what they call the bug, I call it failure mechanism, the rowhammer bug, to gain kernel privileges. And this is directly from their blog post. I would highly recommend, if you're interested in hardware security, I would highly recommend reading their blog post. It's beautiful security engineering, and I copied and pasted some of their sentences. They said they tested a selection of laptops and found that a subset of them exhibited the rowhammer problem, and they learned the rowhammer problem from our work. They built two working privilege escalation exploits that use this effect. One of them is not that interesting to me. It basically takes over the Google native client, essentially a virtual machine. But the other is very interesting. It basically induces the bit flips to gain kernel privileges on x86-64 Linux as a user-level process. What it does is, simplified, it is able to induce bit flips in the page table entries of the process, where the page table entry points to the page table of the process. And if you're able to induce the right bit, flip the right bits, you are able to gain write access to your own page table. And once you gain write access to your own page table, all bets are off. You have full access to the entire system. Now this became famous as rowhammer vulnerability. People started drawing pictures like this. I like this picture. But I like the insight that comes out of some of these Twitter discussions. One of the famous hackers on Twitter basically said it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were So I'm going to go over some of the security implications. Actually, I'll skip these because this is just references for the papers. But there are really interesting security works that built on this later on. These folks from Technical University of Graz, actually these are some of the folks who also later on, they worked a lot on rowhammer, and then later on they went to co-discover Meltdown and Spectre, if you're familiar with those. They basically showed that you could gain unrestricted access to a remote server through the JavaScript. This is actually another paper from Vrije University in Amsterdam. What these folks showed was you could, on an Android phone, you could first profile the memory, figure out which rows are vulnerable to rowhammer, and then by exploiting the deterministic memory allocation patterns of the Android Linux operating system, fool the operating system to allocate a page table entry of your own page table to a location that you know, next to a location that you know is vulnerable to rowhammer. And then you would go and hammer that. As a result, you could actually deterministically gain access to a cell phone. And you could actually download their application. I think they still have an Android application where you could download and get someone to take over your system. So they also show that you could do this on ARM processors. So there are more recent papers where people show that you could do this through a GPU. A GPU is very powerful in actually hammering memory, and using, again, a user-level program through the WebGL interface, you can rowhammer and take over a mobile system. And there are other folks that show that you could do this attack over the network through the remote direct memory access protocol, where you would read and write to some other server's memory. And these two works are actually concurrent from different folks that are doing exactly the same thing. And there may be other security implications, or this may be one solution, but maybe it's not a good solution for this. So let's talk about solutions. Clearly this is a scaling problem. Maybe it could have been avoided if you had a more intelligent memory controller, because if you had some slightly flexible intelligent memory controller that you could run some code on, you could avoid it. I'll talk about that solution. So these are some potential solutions. Make better DRAM chips. Clearly it's been very difficult. Refreshing frequently, we'll talk about that. Having sophisticated error correction codes, and having access counters to count how many accesses you have to a row and then stop at the memory controller level. I believe all of these solutions have issues: cost, power, performance, complexity. In my opinion, it's not easy to, or desirable to employ these solutions. We're going to talk about this refresh. So what's the solution that you could, I believe there are two kinds of solutions. There are chips that are vulnerable in the field. How do you deal with them? And there are chips that we're designing going into the future. How do you deal with these rowhammer errors? If they're vulnerable in the field, refreshing frequently is probably a very good option. And a lot of manufacturers are doing that. This is Apple's security release. They basically increase the memory refresh rate such that the vulnerability to the rowhammer reduces, because you cannot do enough activations with a smaller refresh, with a higher refresh rate. And I like using Apple because they're nice enough to give credit to our paper in their security release. But it's true for actually pretty much across the industry. So refresh rates are increased. But as I said, increasing the refresh rate is not what we want. This is not good for energy, performance, quality of service. We want to actually get rid of refresh as much as possible. So this may be a good solution in the field, but this may not be a good solution going forward. So what's a good solution? This is our solution proposal. It's a probabilistic solution. The idea is very simple. Whenever the memory controller closes a row, it's with very low probability activates the adjacent rows. Let's say 5 out of 1,000 times. And if you're not comfortable with that 5 out of 1,000 times, you could program the memory controller to do it more. But 5 out of 1,000 times actually gives you a very good reliability guarantee according to our results, depending on, of course, how many row hammers you need to do, activations you need to do to induce row hammer. We call this probabilistic adjacent row activation. This is low power, low performance overhead, and it's stateless. It doesn't require tracking which rows you're accessing. Basically, whenever you close a row, you flip a coin, and with some probability, you refresh the adjacent rows. And this, I believe it's an effective and low overhead solution. It could be extended going forward. I'd be happy to talk about it. So how do you actually do this today? So you could actually implement probabilistic adjacent row activation in the DRAM chip or in the memory controller. I'm going to argue for doing it in the memory controller. Actually, it is implemented in some DRAM chips today. The requirement is that you need to have enough slack in timing parameters. So whenever you're doing, let's say, closing your row, whenever you're doing a pre-charge, if you have enough slack in the timing, if the DRAM manufacturer specified that you actually need to wait for longer than you really need to wait, the DRAM chip can inject a refresh to the adjacent rows. Or if you have similar slack in the refresh timing, you could do that. And this is already employed. I don't think this is a very good solution because it requires relying on that slack. Actually, we want to get rid of slack. There's plenty of slack today in the timing parameters that's causing the latency overheads that we see in the memory system. And if you want to reduce the latency, you want to get rid of the slack as much as possible. And once you get rid of the slack, you cannot employ a solution like this. If you're doing it in the memory controller, I believe this is a better place to do it. You get better coordination, but you need better coordination between the memory controller and DRAM. Today, the memory controller doesn't know which rows are physically adjacent. That information doesn't get exposed. You could reverse engineer it with a lot of effort. So it is possible to do it in the memory controller, but maybe there's need for a better memory interface between the memory controller and DRAM. And this is going to be one of the principles that I'm going to talk about later on. Better interfaces, better communication between different components. Okay, that said, this is actually employed in some of the most recent Intel memory controllers, basically except in the BIOS. In the BIOS, you could actually choose between hardware row hammer protection and double refresh. And if you actually choose hardware row hammer protection, you could choose a probability of activation. Although this doesn't this assumes linear addressing as far as I understand. So it may not always fully work if you actually do it this way. So it's better to have better communication between the memory controller and DRAM for this to work. So there's more analysis in our paper, which I'm not going to go into. They're actually really interesting studies. For example, if you want to induce row hammer, it's very data pattern dependent, so you need to set your data patterns. Okay, as I said, industry is writing papers about it too, but I'm going to go. So basically, we need intelligent memory controllers to correct for these errors. And actually, I believe there's nothing really special about DRAM. The very special thing about row hammer is the errors are directly exposed to the programming language, so that you can induce them in a very predictable manner. Because if a bit is vulnerable, it's going to stay vulnerable. So you know that you could induce these errors and take over the system. But these errors exist in any scaled memory technology. In fact, flash memory is a very scaled memory technology. We're actually at much lower technology nodes in flash memory. There's a lot of error correction and error handling mechanisms employed in an intelligent memory controller. And we've been building these controllers. I'm not going to talk about these studies except for referring to some papers maybe. But they actually know how to design these controllers. Flash memory has a flash translation layer that tries to get rid of the errors as much as possible, because flash memory is a technology that doesn't work really well if you don't have a good controller. And we know how to design these memory controllers. This is a recent paper that we wrote based on about 6 to 7 years of research that we've done in the area of flash memory. And if you're really interested in understanding how sophisticated controller mechanisms are, I recommend you take a look at this paper. So a key takeaway is main memory needs intelligent controllers. And I believe the challenge and opportunity for the future is fundamentally secure, reliable, and safe computing architectures. So So let me turn to the future a little bit and talk about some other reliability issues. As I showed you, DRAM is becoming less reliable and more vulnerable. And it's not going to change, it's going to become worse, in my opinion, and I believe we need more studies like this that are looking at large-scale studies. We've been doing studies also, large-scale studies on flash memory failures, and they're also getting worse. And due to difficulties in DRAM scaling, there may be other problems that also appear, or they may be going unnoticed today. Some errors may already be slipping into field. Clearly, read disturb errors, row hammer errors are slipping, but there may be retention errors, there may be read errors and write errors, and others. These errors can also pose security vulnerabilities. I'm going to focus on retention errors because this is really a fundamental scaling problem. If you go to a DRAM manufacturer today and ask the designers, cutting-edge designers, what's keeping them up at night in terms of technology scaling, you will probably get the answer retention or refresh. So why is this a problem? The problem is that determining the data retention time of the cell is getting more difficult as we scale the technology. As a result, I believe retention failures may already be slipping into the field. And we've been doing a lot of studies with our experimental infrastructure. It's one of the first works that I'm going to very quickly cover. So there are two key challenges to retention time profiling. One is data pattern dependence of retention time, and the other is variable retention time. Let's go over this very quickly. Data pattern dependence means that retention time of a DRAM cell depends on its value and the value of the cells that are nearby it. This happens because of electrical interference, capacitance coupling. Basically, when a row is activated, all bit lines are perturbed simultaneously. You see the row over here and the bit lines. When you activate the row, all of the bit lines are perturbed simultaneously. And the electrical noise that you have on the bit line affects the reliable sensing of the DRAM cell. And the magnitude of this noise is affected by the values of nearby cells. Because of bit line to bit line coupling, there's electrical coupling between adjacent bit lines, and also, this is the bit line to bit line coupling, and also because of bit line to word line coupling, there's electrical coupling between each bit line and the activated word line over here. As a result, what value you have, whether you have charge or not charge, how much charge you have in the capacitor determines whether you will get errors or not. So the retention time of a cell depends on data patterns stored in nearby cells, which means that if you want to find how often you need to refresh a cell, you need to find the worst data pattern to find the worst case retention time. And that pattern is actually location dependent. So it's not that easy. But this is not the hardest problem. I think this other problem, the quantum-like effects, are much harder. These are becoming much worse as you reduce the size of the cells. The retention of a DRAM cell changes randomly over time. A cell alternates between multiple retention time states, as I said earlier. And this is because leakage current of a cell itself changes sporadically due to charge trap in the gate oxide of the DRAM cell access bands. This is called trap-assisted gate-induced drain leakage. When the trap becomes occupied, the charge leaks more readily from the transistor's drain, and that leads to a short retention time. And this is an effect that was known since 1987, but it's becoming much worse in existing DRAM technology. And this process appears to be a random process, which means that the worst-case retention time of a cell depends on a random process. You don't know how long a cell will retain data. And you need to find the worst case despite this. And our experiments show that you may need to test a DRAM cell for days and days to actually see the worst case, sometimes much longer. So it's not easy on the manufacturer's end to actually determine these. So we've done a lot of studies. I'll go through this very quickly. Basically, newer device families have more weak cells than older ones. If you look at this as the retention time, we do it at low temperature. That's why you see this high retention times over here. And this is a fraction of cells that have retention time less than the x-axis value. If you look at an older technology, the curve looks like this. If you look at a newer technology of the same manufacturer, the curve shifts to the left, meaning that more cells fail at smaller retention times. That's true for other manufacturers as well. And this is an example of a variable retention time of the cell. You basically test the cell's retention time over some number of hours, and the cell basically changes retention time states. Sometimes it can retain data for only 2 seconds or so. Sometimes it can retain data for much longer. That's our testing boundary, so it doesn't see errors after 6.1 seconds over here. So this is another example from a particular manufacturer. If you look over here, this is the minimum retention time of the cell that we've seen, and that's the maximum retention time of the cell. If you actually don't have the variable retention time phenomenon, you would expect a curve that's linear, x equals y curve. You would expect this if there's no variable retention time. But if you look at this, most of the failing cells exhibit variable retention time. If you look over here, many failing cells jump from very high retention time over here to a very low retention time, minimum retention time. So this phenomenon is increasing. It's becoming difficult to actually find the retention time of the cell. And if you say that actually this is the DRAM manufacturer's problem, it's not that easy, because it turns out after you take a DRAM chip, assuming that the DRAM manufacturer perfectly found this with a lot of testing cost and gave you these retention times, then you can actually reduce the refresh rate significantly. If you take the chip and solder it on a DIMM, you expose it to high temperatures, and you change the retention time profile completely. As a result, you have a system problem as opposed to a manufacturer problem. So the system needs to somehow overcome these. And as I said, industry is writing papers about it too because of this reason. So we've been actually looking at how to mitigate this. I'm not going to go over this in detail significantly. I believe this causes actually security vulnerabilities which have not been exploited yet, but that could potentially be exploited. Our solution direction is, again, an intelligent memory controller that dynamically figures out the retention times and adjusts the refresh rates dynamically. So basically, we found that testing alone cannot detect all possible failures because you need to test for really long times. So you need to use error correction codes. And if you use error correction codes and on top of that online profiling of the retention time, you can be much more effective, but this degrades performance. So you need to actually design this nicely. So you can actually use testing to reduce ECC strength. So let's take a look at this pictorially at a very high level. Basically, you protect DRAM with some ECC. I think this is the trend going forward. Maybe with strong ECC. And you periodically test parts of DRAM. And you mitigate errors and reduce ECC by changing the refresh rate. If there are some weak rows, you increase the refresh rate and reduce ECC. If there are some strong rows, you reduce the ECC and maybe increase the refresh rate also. So you can actually adjust the ECC and refresh rates. Okay, basically you can run tests periodically after a short interval at smaller regions of memory to reduce the testing cost. And we have actually a lot of works that talk about the cost of this profiling, but I'm not going to go over this in detail. If you're really interested, I'd be happy to talk about it. This is one of the latest works that you looked at. Manish Patel, who's also a UT Austin ECE graduate, did this work. And this analyzes all of these variable retention time and data pattern dependence phenomena in the LPDDR4 chips. It basically looks at the complex trade-off space of retention time profiling. And it's essentially a fast and robust profiling method. If you want to enable a refresh interval X, you want to test the device at a refresh interval, let's say X plus Y, at a much higher refresh interval. And if you want to do that at temperature T, you want to test the device at a temperature T plus U, for example, at a much higher temperature. Okay, and there are a lot of other interesting things that you can do that I'm not going to talk about over here. So let me talk about, before we conclude, conclude the first lecture, let me talk about some of the principles that we can potentially use to keep future memory more secure and more reliable. So this problem is not going to get easier. I think flash memory is actually worse. Some of the emerging memory technologies are actually going to become worse, if they're not worse today. Even though they may not have the refresh problem as bad as DRAM, they may have other problems. So I believe we need to have more principled designs, fundamentally secure computing architectures, predict and prevent such safety issues. So if you recall the bridge over here, you may actually think that we actually know how to design these bridges, but we've seen a lot of these examples. This is Seoul in 1994. Another example, this is Minneapolis. This is Genoa very recently. I don't think we should run into those problems. Actually, these were real reliability problems that led to safety and security issues because there were real people who were killed in these bridges. And I think I liken the reliability problems in computing systems to these bridges because computers are no different from bridges because we rely on them on everything, and we're going to rely on them even more going into the future. So how do we architect for reliability and security? I don't think this is easy, and I don't think I have all of these nailed down yet. Basically, I believe we first need to understand. We need to develop methods for vulnerability modeling and discovery. We need to model and predict based on real device data and analysis. And I think this is really important because something like Rowhammer, for example, it's very difficult to model in simulation. You really need the real device data for that. We need to understand the vulnerabilities and develop reliable metrics. These are all bullet points over here, but these are all big research areas, I think. Like what are the reliable metrics that you develop to understand the vulnerabilities. On top of that, we'll need to architect. We need to have principled architecture with security as a key concern from the very beginning. We need to have good partitioning of duties across the stack. We shouldn't push solutions to a particular level. Like solving the row hammer problem inside the DRAM chip, I don't think is a good solution. If you actually put it in the memory controller, it's a better solution. Maybe the refresh problem should be solved at higher levels of the stack with good information communicated across the components. Of course, we cannot give out performance and efficiency while we're doing that, and I believe we need to have patchability in the field. If you have an intelligent and patchable memory controller, even if we have issues that are discovered in the field, perhaps we can reprogram the memory controller to fix the reliability issues that we discover over time. And on top of this, I believe we need to have principled design, automation, online testing methods that are designed for security from the ground up, have security as a key system design concern. Of course, we need to have high coverage and good interaction with other system reliability methods. I don't have time, but I'd be happy to talk about this in more detail. So I think we've been doing this understanding and modeling with experiments in the DRAM space. That was one of our goals, and the flash space, but there needs to be more. And if you're really interested in flash memory, I'd be happy to talk about it, as I said, over here. There are vulnerabilities in the flash space also. And these are some recent papers that we've done in the area on 3D NAND flash. And there are more over here. Yukai was a student who did a lot of flash memory work, as you can see over here. So let me talk about two other solution directions before we conclude. I think we still have time, right? Okay. Yale's saying -5 minutes. But he knows me, so. So there are two other solution directions that I believe are really, really interesting. One is new technologies. There's a caveat here. We can replace or more likely augment DRAM with a different technology that doesn't have these problems. Good luck with that. There is no technology, scaled memory technology that doesn't have problems, in my opinion. But we should strive for it. Non-volatile memories are an example. At least they don't have a refresh problem as bad. Flash memory doesn't have a refresh problem as bad, but we still refresh flash memory today to get rid of the errors that we have, to improve the lifetime. So every memory requires some sort of refresh. The question is how bad is it? But there may be other problems. So I believe this is a very, very promising solution direction. The other solution direction is embracing unreliability, at least for applications where you could embrace it. What does this mean? Maybe we can design memories with different reliability guarantees and store data intelligently across them. Not all memory has to be completely reliable, but maybe for critical data you need to have really reliable memory. This may lead to a scalable solution because if most of your memory you can get away with less reliability, now you can keep increasing the size of your memory at low cost. But of course this requires good partitioning of data and understanding of your data, which means that if you want to employ both of these solutions, you need to have co-design across the hierarchy. So we cannot solve the problem at this level or at this level or at this level. You really need to think across the stack right here. Let me talk about this very quickly. We've done some studies over here. So what do we mean by embracing unreliability? So applications have different kinds of error tolerance, both at the application level and the data structure or data level. So if you look at an application, some data may have very high vulnerability to errors. If you have a bit flip, your system might crash. Whereas if you have a bit flip on some other data, you may not care. Maybe a pixel changes on your screen, but you don't care about that pixel. Its effects are minimal. Vulnerability is minimal. If you can classify your data this way, perhaps you can map your data, vulnerable data, to reliable memories and tolerant data to low-cost memories. So it's essentially a hybrid memory system where you design the reliable and low-cost memories separately. We call this heterogeneous reliability memory. And there's a huge design space, of course, over here. What is reliable and what is low cost? We tackled some of this in this paper. I think this is an early work. And of course, there may be shades of gray in terms of vulnerability of your data, in terms of criticality of your data. But once you do this, you can gain benefits. So we did this in 2013 or so, collaboratively with Microsoft. One of my students, Hishin, who recently graduated, also went to Microsoft and examined what happens if you actually do this partitioning on multiple workloads, including their web search workload. So at that time, our motivation was all of the memory in the data center has error-corrected codes. And this costs a lot of power, energy, and cost. So if we get rid of some of that error-correcting codes in memory, some memories with error-correcting codes, maybe we can reduce the cost and improve the efficiency of the data center. And it turns out that if you do coarse-grained partitioning of your data in the web search application, you can do that. You can get rid of a lot of the ECE memories in the system and reduce the server hardware cost by about 4 to 5%, while still achieving a good availability target of 99.9%. And as I said, this is early work. There's a lot more to do in this area because there's a huge design space in terms of both how you would design, how you would understand the vulnerability at the higher levels, programming level, and how you would communicate it, and also how you would design the underlying memories to be different, and how you do the mapping. Okay, let me conclude. Hopefully I've convinced you that memory reliability is reducing. Reliability issues open up security vulnerabilities as well. And these are very hard to defend against once they're found in the field and you don't have good mechanisms to defend against them. Rowhammer is just one example. I believe it's the first example of a circuit-level failure mechanism that caused a widespread system-level security vulnerability. Its implications on system security research, I believe, are tremendous and exciting, and there are very, very interesting papers that are coming up pretty much every month related to Rowhammer. And I think this is just one example. There's more that is coming up in memory. The good news is we have a lot more to do to keep the systems more reliable and secure, but we need to be more principled, in my opinion. We need to somehow develop methodologies that are much more solid to understand and do modeling and do good architecting and good design and testing. So essentially we need to design fundamentally secure, reliable, and safe computing architectures. But the takeaway is I believe we cannot do that in memory without intelligent memory controllers. So we're going to talk about that next in the next lecture. I'd be happy to take questions now.
Any questions for Professor Mutlu?
So you proposed a lot of solutions with these memory controllers. But what do you think the granularity of those controllers should be? I understand it's application dependent, but can you just give a general comment on that?
What do you mean by granularity of the controller?
So, for example, you don't want 1 byte of metadata for 1 bit of data, right?
Say again?
You don't want 1 byte of metadata for 1 bit of data you actually.
Oh, I see. Basically for error corrected codes, you're thinking, or?
Like just general for your intelligence.
Well, I think it depends. For example, if you want to defend against Rowhammer, I don't think you need any metadata if you use the probabilistic adjacent row activation solution. I think we should strive for solutions that are extremely efficient. If you can get away without metadata for Rowhammer-like mechanisms, I think that's a good idea. In fact, I did talk about this, but error correcting codes, in my opinion, are not a good solution for Rowhammer, because error correcting codes are a good solution when you don't know the source of the errors, or source of the errors are not predictable. So if they're random, error correcting codes are great. But if the source of your error is very predictable, like access pattern dependent, you want to get rid of the metadata, you want to get rid of ECE, and you want to solve the problem with a much more efficient solution. So I don't think there's a single answer, frankly. It really depends on the failure mechanisms. And actually, if you look at flash memory, it's very successful at doing that. It has a lot of error correcting code because the technology is very unreliable, it's very prone to random errors, but it employs a lot of other techniques like voltage optimization or refresh and a combination of different optimizations to actually minimize the errors. And those errors are mechanisms are targeted toward the specific error mechanisms. Yes.
Yeah, so a lot of what you talked about is about handling everything in hardware, right? An intelligent memory controller or below, or you profile application vulnerability and then you differentially map it across these things. What about the other way around, in which you reduce the hardware complexity, expose more to software layers, and let the software deal with it?
So I think the last solution that we discussed, the application vulnerability, is putting a lot of burden on the software actually. You still need complexity in the hardware to have the heterogeneous design space.
Are you thinking about the mapping being done by software explicitly versus an intelligent memory controller?
You could do it both ways, but when we did it actually, it was based on software. Yishin did the entire mapping by hand actually in that case. I believe you need to have semantic information from the programmer to be able to do a lot of that. But I don't take sides on hardware and software. I think we need to really examine the full space. When it makes sense, we should really do the software solutions also. Well, I'm not sure if Rowhammer is... I think it really depends on the error mechanisms. Right? I don't think we want to expose Rowhammer-like issues to software.
You're saying that all memory cells need to be refreshed?
I'm not sure if I said that, but they do need to be refreshed, yes.
No, how do you refresh an SRAM cell?
Oh, all DRAM cells. Yes.
So maybe we need figure out a new kind of cell.
Yeah, that's the other solution direction that I mentioned, like emerging memory technologies. I agree with you. If there is a cell, that's great.
The reason why rowhammer is a problem is because of the physics. Is there any way we can invest in the physics so that that adjacent row doesn't get clobbered by hammering the other row?
I would love to have an answer, but I don't have the expertise in that area. But I think the difficulty is, I don't know. I mean, who knows, right?
I'm just a student, so.
So the difficulty is, at least from the circumstantial empirical evidence, we have not gotten rid of read disturb errors in scaled memory technologies, because SRAM has these errors, rowhammer-like errors. Flash memory has these errors. Hard disks have these errors. At least at the cost levels we're operating at in the systems we're designing, it seems like we're not using that physics, even if it's available.
At some point toward the end of your talk, you talked about memory doesn't have to be quite as reliable as other memory. It came across to me as approximate computing being couched in a slightly different flavor. And as you well know, I've never been impressed by the fact that you can look at a picture on a screen, half the cells can be giving you the wrong information and you can still identify.
Yeah.
So that's not the interesting problem with respect to approximate computing.
So I agree.
It may not be the interesting thing with respect to your reliable memory versus the unreliable.
Yeah, I think it's not the interesting thing. I think we still need to have some error bounds in terms of reliable versus unreliable. I'm not suggesting just randomly change the memory such that it doesn't give you any guarantees. I believe the principal way of doing that would be designing memories with different reliability guarantees. Probabilistic, potentially, because everything is probabilistic. And then presenting this as a software so that the software can take advantage of that.
I think it's an important problem, by the way, and I don't think it's us that are going to solve it. I think it's the algorithm people, which is that can I take a problem and partition it into parts so that part of it needs to be right on the money and other parts can be approximate and therefore be done much faster without bad implications. But the part that needs to be exact. How we take a problem and break it down to be able to do that, I have no idea. That's why I say it may be the algorithm people.
Yeah, I agree with you. I think that's why I said it's really a software problem. I think we can only, the hardware folks can provide memories with different reliability guarantees.
Your iCache, you want to make that reliable, or does it matter whether one bit is flipped and so an add becomes a subtract?
There you go. So
Any other questions? Okay, tomorrow at 3:30. Thank you very much.